Hello everyone! In this lecture, I will give you the definition of a row echelon matrix and I will mention about what its importance is and the terminology related to row echelon matrix and give some examples which are row echelon matrix or which are not row echelon matrix. And following that, I will start to talk about Gaussian elimination method, which is one of the most important methods that we use so as to solve a given system of linear equations, and also it is one of the key concepts in any linear algebra course. Alright then, after summarizing what is waiting out for you in this lecture, we can start with the basic definition of what a row echelon matrix is. And before even that, if we actually already have learned about what an upper triangular matrix is, right, in our previous lectures, and what it was is simply, it is just a quick reminder before giving the definition of a row echelon matrix. For instance, a matrix like this, so just make up some values, right? And a matrix like this, as I wrote down here on the whiteboard, is called an upper triangular matrix. Why is that? Because we know what the main diagonal is, and when we draw the line that represents the main diagonal, we look at the values right below the main diagonal, and if they are all equal to zeros, then this matrix is called an upper triangular matrix, and its technical definition is like, for all I is greater than j, if aij's are equal to 0, then this matrix is said to be an upper triangular one. And here I represents, well, let me erase it a little bit. It doesn't look fine, so let's say aij, alright, so okay. And I here represents the number of the row number, and j represents the column number. And what I mean when I is greater than j, for instance, for this 3 by 3 matrix where we have 3 rows and 3 columns, I mean the entries in the matrix below the main diagonal, right, which are actually a 2 1, a 3 1, and of course a 3 2, right? These are the entries where the value of I is greater than the value of j, right? If I write it down, this is 3 2, this is 2 1, this is 2 is greater than 1, and again 3 is greater than 1, you see, and 3 is greater than 2, because the definition of an upper triangular matrix is this. So now I will define this concept from a more technical point of view with the name of row echelon matrix. And in the context of Gaussian elimination method, this is what we are going to use. We will try to convert a system, or the matrix form of the system, say it that way, into that of known as the row echelon matrix form. Okay, get back to our point and let's define technically what a row echelon matrix is. Here is the definition. If a matrix is a row echelon matrix, then it needs to satisfy the following two properties. Or in other words, a matrix is said to be a row echelon matrix if all of these two properties are held. Okay, what are these properties? Well, first, all non-zero rows must be above 0 rows. And by the way, what I mean by the non-zero row or 0 row, a non-zero row is a row where, well, it is a row in a matrix where at least one of its entries is not equal to 0. So if there is a non-zero, at least a non-zero element in the row, then that row is called a non-zero row. For instance, in the following example, let's give some numbers to our matrices. So this is the first matrix and this is the second one, and say this is the third one. All right, so just number them, give labels to them, so that if we assign labels, we know on which matrix we're talking about. Okay, well, now say I'm talking about matrix 1. So is there a 0 row? No, because a 0 row means a row where all the entries in that row are equal to 0. So there is no non-zero element. But all the rows in the first matrix are non-zero rows, because each row, when I read through each row separately, I can see that simply, you see, for instance, the first row 176 and second 0 1 minus 2 and 0 0 4, at least there is one element which is not 0, right? So there is no 0. How about the second matrix? Well, in the second matrix, if we number the rows from top to bottom, first, second and third, we see that the row in the bottom, so in other words the third row, involve only 0 values. It consists of only zeros, so it's called a 0 row. But the first and second row are non-zero rows because they have at least one element which is different than 0. Okay, and this is the terminology, some of the terminology meaning about the meaning of a non-zero row and a 0 row. And okay, get back to our point. The first property that must be satisfied is that all non-zero rows must be above 0 rows. In other words, if there is a 0 row, it must be below all the non-zero rows. This is another way around to say the same thing. Okay. And the second property is this. The number of, I use the hash symbol to denote the number, okay, the counting, okay, the number of leading zeros at k plus first row is strictly greater than the leading zeros at the kth row. So what I mean by that? As you notice, k plus 1 is the row right below the kth row if we number the rows from top to bottom. This is actually by convention what we do. Okay, so in other words, what about the leading zeros? What do I mean by saying leading zeros? And leading zeros, so this is the thing. We count the number of zeros in a row up to some element which is not equal to 0. For instance, in the first matrix, in the example, if you look at the first row, there is no 0, right? So there is no leading 0 here. But when we look at the second row, if we read the second row from left to right hand side, we see it starts with a 0. There is 1 0, right? And the first non-zero element is 1. So the number of the leading zeros at the second row, or in the second row, is only 1. And how about the third row? And we have 2 leading zeros in the third row, right? Why? Because I just simply count the number of zeros from left to right hand side up to the point where I have the first non-zero element in that row. So the first non-zero element in the third row of the first matrix is number 4, and the real value 4. And before that we have 2 successive, right? We have 2 consecutive zeros, so the number of leading zeros are 2 in this example. So getting back to my point, what this second property says, okay, we count the number of zeros, leading zeros, at the k plus first row and the kth row, and it must be strictly greater than. What do I mean? For instance, if I look at the first row, I have no 0. and say k is equal to 1, okay? And then k plus 1 is equal to 2. So in the k plus 1 row, k plus first row, in other words in the second row in this case, we must have at least 1 0, right? Because it must be greater than the row. The number of leading zeros must be greater than the row right above it. So in the second row, I must have more zeros than the first row. And in the third row, I must have more leading zeros than the second row. And this is the case actually when we look at this first matrix carefully. In the third row, I have 2 leading zeros, and in the second row, I have 1 leading zeros, which means that we have strictly greater than, in terms of course, the number of zeros, it is strictly greater than the above row, right? If it were like this, if this weren't 0 but something different than 0, for instance, if it were a 2, for instance, then the second property wouldn't have been satisfied. Why? Because now in the third row and in the second row I have equal number of zeros, which is not enough for us to satisfy the second property, because it should be strictly greater, right? There is no equality sign here. You notice that, right? There is no equality. So I erase them quickly to confuse a misunderstanding. And again, I make my value here, again, turned into 0. It is original number, right? So it was 0. Okay. All right then. Let's go through our matrices, see which one is in the row echelon matrix form and which is not, or which aren't, okay? The first matrix, look at the first matrix. All of the rows are non-zero rows. So there is no 0 row. So the first property automatically is satisfied, right? So we just take into account the second property. And is the second property held for this matrix? Yes, it is. Because I count the leading zeros at each row, and for the consecutive rows, the row below the other one should have strictly greater number of zeros in comparison with the one above it, right? So what I mean, in short, second row has 1 0 and the first row has no 0, which means second row, the number of leading zeros at the second row is strictly greater than the leading number of zeros in the first row. And the same thing holds for the second and third rows. We have 2 leading zeros in the third row, whereas we have only 1 leading zero in the second row, which is sufficient to say that the second property is satisfied. And therefore, the first matrix is in the row echelon matrix form. And it's the row echelon matrix. Another quick way that is maybe even simple to say that it is in the row echelon matrix, or in other words, given a matrix, to say that it is in row echelon matrix form, we can do the same strategy like this. For instance, we draw the main diagonal, right? And look at the values right below the main diagonal. If they are all zeros, then we call that this is in an upper triangular form, which means that it's in the row echelon matrix form as well, right? But the problem is that, as you might notice, this is a square matrix. What I mean is that, what is a square matrix? It's the 3 by 3 matrix, right? We have 3 rows and 3 columns in this first example, which means the number of rows is equal to the number of columns, and that is what is called a square matrix. And a square matrix is a kind of matrix where the number of rows is equal to the number of columns, okay? It's an n by n matrix, in other words. But if the number of rows is different than the number of columns, then it is not a square matrix. So this strategy does not work on matrices which are not square. For instance, for the second example, we have a 3 by 4 matrix. We have 3 rows but 4 columns. This is not a square matrix, so I can't draw the main diagonal here, right? Okay, so the first one is in the row echelon matrix form. Put a tick on it. Okay, how about the second one? I checked to see whether or not these two properties given above are satisfied, and the first one is automatically satisfied because we have only 0 rows, right, which is the third row in the second example, in the second matrix, and the third row is below all other rows, right, which are non-zero rows. In other words, the 0 row, the only 0 row, is placed below all the non-zero rows in the second matrix, so the first property is satisfied. How about the second one? Well, in the first row we have no 0, so the number of leading zeros is equal to 0. In the second row we have 2 zeros, strictly greater than the first row, right? And in the third row we have 4 zeros, which is strictly greater than 2. In other words, from the row right above it. So there is no problem for the second property. The second property is also satisfied. So this is the matrix. The second matrix is also in the row echelon matrix form. How about the third one? Well, I'll look at the situation. There is no 0 row here, so the first property is satisfied. There is no problem with that. But how about the second? If you notice that we have a 1 leading 0 here in the first row at the top, so but right in the row right below, okay, look at the row right below the first row, so we have no 0 here, so the number of zeros, leading zeros, is 0 in the second row of third matrix. But this means that the second property is not satisfied, because if this were if this matrix were a row echelon matrix, then the number of leading zeros should have been strictly greater than the number of leading zeros in the first row. But this is not the case for the third matrix, and therefore it is not a row echelon one. By the way, well, that's right, it's not a row echelon, but can we convert it into a row echelon matrix? Let's raise this and see what can we do about it. So is it possible? So this is not in the row echelon form, but is it possible to convert it into a one which is row echelon? Yes, that is. There is a way. When we know in the previous lecture we have learned about 3 elementary operations that would allow us to convert any arbitrary system into that of an equivalent system. And by saying equivalent system, I mean a system which has the same solution set. In other words, without changing the solution set, it is possible to perform some operations on the system of linear equations or on its matrix form to convert it into an equivalent form where we can have a simple solution, right? Or in other words, we can simply solve the equation. So in this case, for instance, if you notice that if we replace the first row by the second row, then what we get? Suppose I replace the first row by the second row, and also we know that we have 3 elementary operations that are allowed us to perform. And what are these? We can swap 2 equations, and we can multiply an equation by a real value and then replace it by this newly found equation. Or in the third case, we again multiply another row by a real value and add it to itself and replace this row by the newly found equation that we've just found or we have created, right? So in the third matrix, by simply replacing the first row and second row, what we get without changing this solution set, if of course this matrix represents a system of linear equation, right? 0 1 minus 4 2, and I don't do anything on the other rows. In the third row or in the fourth row, we don't have, or we don't perform any operation, right? I just write them as it is. Okay, now what we get, as you might notice, this is a 4 by 4 matrix, and if I draw the main diagonal, you see below the main diagonal are only the 0 values, which means that it is an upper triangular matrix, or in the row echelon matrix form, right? So just a simple modification made this matrix a row echelon one. Okay, how about the fourth one? Okay, when I look at the fourth one, the problem is that it does not satisfy the first property. There is a 0 row right over here in the second row, because all of the entries in the second row are equal to 0, which means this is a 0 row, and a 0 row must be below all the non-zero rows, and first row and third row are non-zero rows, and we should replace this second row with the third row. And we show this like, for instance, if I want to replace second row by third row, where R2 represents the second row and R3 represents the third row, I can simply use a doubly directed arrow like this. You see, this is to indicate that I replace our second row by the third row. I just switch their places that they hold in the matrix, right? That's what it is. Minus 7, 6, and 7, and the rest is the same. Okay, I just modify the locations of the second and third rows. So this is 6, and now what I get? Again, I have a 3 by 3 matrix, a square one. When I draw the main diagonal, you see this is the case. So now I converted it into the row echelon form. But in the beginning, of course, in its original version, it wasn't a row echelon matrix, right? Okay. This is actually what a row echelon matrix is, and how can we understand that a given matrix is in the row echelon matrix form or not, and if it is possible to convert it into the row echelon matrix form. And yes, the answer is it is possible by simply performing 3 elementary operations. Alright then, before proceeding to the more technical topic, which is of course applying the Gaussian elimination, before of course defining what the Gaussian elimination is and then applying it to solve a given system of equations, just a quick reminder. I would like to remind you how can we convert a system into an augmented form, or vice versa. In other words, if we have an augmented form, then how can we convert it into the system of linear equations? Suppose we are given the, let's say, just make up a matrix. Well, we have already found this, right? It wasn't a row echelon form, but by a simple and a single operation, just performing a row swapping, I now have a row echelon form. And if this is an augmented matrix of a given system of linear equations, then what it means? If you remember, well, of course, before proceeding to applying Gaussian elimination method, I need to quickly remind you how can we express an equation system in the augmented matrix form. Suppose this is the system of linear equations given to us. Okay, suppose 7c is equal to -1. Okay, and 4a plus 6b plus 5c is equal to 4, and minus 3a minus b plus 2c is equal to 3. Suppose this is the system of equations given to us, okay, to solve. Okay, let's make it even simpler. Okay, let's do it this. Okay, now I have a system of linear equations, right? But how can I represent this system, the same system, in the matrix form? If you remember, how would we do that? Okay, we have what is called an augmented matrix, right? So here is the way we create an augmented matrix. What am I doing? What are the unknowns? First of all, I determine by looking at the system of equation what are the unknown variables, what are the coefficients, and what are the right hand side values. And the unknowns, how can I understand what are the unknowns, is that I look at each equation in the system, and the repeated values here, a, b, c, as you might notice, right, they are called the unknown variables, because what I am trying to find is this 3 tuple for this equation, because I have a 3 by 3 system in this example. I have 3 equations and I have 3 unknowns, right? Okay, then how can we convert the system into its equivalent augmented matrix form representation? Okay, I look at the coefficients. Here is the coefficients of a is 1 in the first equation, and when I look at the first equation in the system, the coefficient of a is 1. I just write the coefficients of unknown variables from top to bottom. So I start with the first equation. The coefficient of a is 1. The coefficient of b is what? Is 3. And the coefficient of c is 7, right? But so far, I just write the coefficients of the unknown variables on the left hand side, right? And only for the first equation, of course, for the timing, but I will continue to write for the other equations as well. Okay, but there is one thing missing, and what is missing is the value on the right hand side, and I don't forget it, right? And either with a dashed or a dot line to indicate that the value right to the value to the right of this dashed or dotted line is the value on the right hand side of the equation, right? For instance, minus 1 in this case. How about the second equation? Again, I look at the coefficients 4, 6, and 5, and I don't change the order, right? I write them in the same order given in the equation, because if I change this order, I can't write 6, 4, or 5, or 5, 4, or 6, right? Because then I would be mixing the coefficients of the unknown variables, which means that it is not the same system. Okay, 4, 6, and 5 are the coefficients of the unknown variables in the second equations, and right hand side value is 4. And again, minus 3, minus 1, don't forget the negative sign, because the coefficient is now minus 3 and now minus 1, right? In the third equation, the coefficient of b is minus 1, so don't forget the negative sign, and 2, and right hand side is 3, right? So we have a 3 by 3 augmented matrix form. Sorry, 3 by 4. I forget that. Sorry about that, right? It's 3 by 4. Why? Because the number of rows now is 3, right? We have 3 rows. The first row, the second row, and the third row. Whereas we have 4 columns. This is the first, and this is the second, and this is the third, and this is the fourth column, right? This is the column, right? This is the first column, right? This one. And this is the second column, right? And this is the first row, right? This is the thing that works. Okay, we have a 3 by 4 system, which means we have 3 equations, right? And 3 unknowns, 3 unknown variables. We don't count the right hand side values, right? The fourth column represents the values on the right hand side of the equalities, right, of the equations. Okay, now actually we are at the exact point to explain what Gaussian elimination method is and how it is performed on a given system of equations. Okay, then now it is exactly the right time to bring the pieces together to see what we have done so far. Okay, suppose, here's the thing, let's think about that. Suppose we are given, well, by the way, why don't I use this equation, right? Yeah, that's right. Why don't we just simply solve this equation? Alright, and of course before that let's define Gaussian elimination method. And Gaussian elimination method is this: we have an n by n system. Alright, we're given an n by n system, and for this n by n system our main goal is to convert this system into a matrix form which is row echelon matrix, and then by applying back substitution method solve the system and find the solution. This is actually what is called as Gaussian elimination method. So in other words, we are given an n by n system of linear equations, and we then write our system in the matrix form, in the augmented matrix form. And if it is a row echelon matrix, then everything is fine because there is nothing for us to do to solve the system. We can simply use back substitution. But if it is not in the row echelon matrix, which is usually the case, of course, then our main goal is to try to convert our matrix into an upper triangular one, in other words into the row echelon form, and then by substituting back we solve our system. Okay, so this is actually what Gaussian elimination method is. And to apply this method to solve the problem of solving a system, we need to follow some basic steps. So the first step is, we are given an n by n equation system, right? We have a system, n by n system, and first of all we represent the system in the augmented matrix form. So this is the first case. These are the main steps that we need to follow to apply Gaussian elimination method. Augmented matrix form, right? So we first write our system in the augmented matrix system form, okay? Augmented matrix form. And then what? After converting it into the augmented matrix form, then we check to see if it is in the row echelon form or not. If it is in the row echelon form, then it is simple to see the result, right? It's very simple to find the solution. We have done it before in previous lectures in the upper triangular system form, right? It is simple. Just we start at the row, at the last row actually, and then find the unknown variable and move one row above and find the other unknown, and then move one step above and find the other, and in this manner we found simply all the unknown variables. It was just like solving one equation in one unknown variable, and this is the main reason why we tried to convert our system into the upper triangular, into the row echelon form. In other words, we reduce the complexity of solving such a complicated problem into that of one which is very simple to solve, such as solving an equation in unknown variable, right? Okay, and if it is not in the row echelon form, then convert it into row echelon form, right? Convert the augmented matrix convert augmented matrix into row echelon form. And then if we have a row echelon form, then use back substitution to find the solution. Back substitution, right? Use back substitution to find the solution. And whole this process is called the Gaussian elimination method to find the solution. Okay. Okay. Now, let's do this. Now we know the basic steps in order to solve a system of linear equations by using a technique called Gaussian elimination method. Okay. So what we need to do is just, we are given an m by n system where m is the number of equations and n is the number of unknown variables, and we'll try to find an n tuple that satisfies all the equations at the same time, right? And then after creating our augmented matrix that corresponds to the system, we check to see if it is in the row echelon form or not. If it is in the row echelon form, then it is very simple to solve, right? By starting at the last row and making our way to the top row one step at a time. So we know each unknown variable in an order, and it is very simple. But if it is not in the row echelon form, this is usually the case, then we will try to convert the augmented matrix into the row echelon form. And how will we do it? Well, we will apply what we have learned in the previous lecture, the elementary operations, right? Elementary row operations. We have three elementary row operations. By applying them, we will convert our matrix into that of a row echelon form, which is equivalent to the original system. In other words, without changing the solution set, we turn our original matrix that represents the system into one which also has the same solution set. And then after having a row echelon matrix, in other words, after reducing our matrix to the row echelon one, then simply apply back substitution method and find the solution. This is the basic steps. Okay, we got to follow. Okay, let's do this. See how Gaussian elimination method works. We already have the matrix. Okay, but before doing that, well, maybe actually while doing that, we can also see that. Okay, this is the matrix we're given, right? In other words, this is the system. Suppose we are trying to solve the system by applying Gaussian elimination, or we try to find the solution set via Gaussian elimination method for this given system of linear equations. A plus 3b plus 7c is equal to -1, and 4a plus 6b plus 5c is equal to 4, right? Okay, then how are we gonna do? We have the augmented matrix over here, right? We already formed augmented matrix that corresponds to the original system. Now what we try to do? Okay, so the thing is, we start with the first row by finding the very first non-zero element in the first row. And in this case, what is the very first non-zero element in the first row? This is 1, right? And this special element is called pivot, and this is the actual pivotal element. This is the magical name given while applying Gaussian elimination method in a matrix form. Okay, well, we start with the first row to find what the pivot element is, and the pivot element in the first row is the one which is non-zero. Okay, the first non-zero element. Why? And why meaning that the first non-zero element is that from left to right hand side. Okay, so I look at the values from left to hand, from left hand side to the right hand side. In the first row, this is 1. Okay, okay, what are we gonna do? We know that the number of leading zeros below this row, right, below the pivot element, must be equal to 0. So I need to convert this value into 0, as well as I need to convert this value into zeros, so that in this manner I will have one leading 0 in the second row and one leading 0 in the third row. But this is not enough to have a row echelon matrix, because right, the number of leading zeros now is strictly greater than the number of zeros from in comparison with the first row. But in the third row I have one leading 0 and I have one leading 0 in the second row, but this is not appropriate. What I need to have is I should have more zeros in the third row than the second row. So then I continue with the second pivot element. When I am done with the first row, I pass to the second row and find the pivotal element in the second row, which is the first non-zero element in the second row, and then find that element and convert the values below that element into 0 and continue that way. Let's see if this strategy really works. Okay, let's start with the first pivot element. What should I do? Well, this is pretty much this symbol I just draw represents the, of course, equivalence, right? So I try to convert our augmented matrix into an equivalent form. Okay, and the operations I will be doing will be represented above or below this symbol, this tilde symbol, this wave-like symbol. Okay, and what are the possible operations that are allowed for me to perform? Well, the first thing is, for instance, I need to change the row R2, row number 2 and row number 3, right? To avoid confusion, I write one of them here and I wrote one of them right over here. Okay, I replace R2 with what? You remember? I can multiply another row and add it to R2. So this way I wouldn't be changing the solution set. So I can add R2 to something, and this something can be a row multiplied by a scalar. In this case, I want to convert the value 4 into 0 by using row number 1, because the pivotal element is in row number 1 for the time being, right, in the first iteration. Okay, so by which value should I multiply? In other words, if I multiply the first row by -4, okay, by -4, which means that multiplying each values in the first row by -4 and then sum it or add it to row number 2 and replace row number 2 by the result, or by the resulted equation that I've just found. And for R3, third row, now what should I do? To convert the value -3 into 0, again I replace R3 with or by R3 plus something else, and this something should be related to multiplying the first row. And if I multiply the first row by 3 and add it to third row, then I can reach to my goal. So let's see what I get. Suppose I perform this operation, and by the way, I use the third elementary operation, right? In other words, I added row 3, row number 1 multiplied by 3, and replaced the value I found here by R3. So then what I get? I have not changed anything in the first row. The first row remains unchanged as desired, right? I don't want to lose my values that already satisfy the row echelon matrix form, so I keep them. Okay, how about second row? Second row plus minus 4 R1. So multiplying the first row by minus 1, we got here minus 4, and adding it to R2 we got 0. Minus 4 times 3 minus 12, add 6 to it, it's minus 6. And minus 28, adding 5 to it, minus 23. And multiplying the first row minus 4, we got 4 here, adding to row 2 we got 8, right? So this is the second row. How about the third row? I add the third row, the first row multiplied by 3. Okay, so I got 0 in the very first entry of the third row, and then I got what? 3 times 3 is 9, plus minus 1 is 8, right? And 3 times 7 is 21, plus 2 is 23, right? And minus 3 times minus 1 minus 3, adding 3 is 0, right? I got this. Right. Now, after the first iteration, I got this matrix, okay? And you see, I am slowly approaching to my goal by using the first pivotal element, which was 1 in the first row. I turned the values below the pivotal element into 0, right? How about now? Now I pass to the second row and I read the values in the second row from left hand side to the right hand side, okay? And find the first non-zero element, which is in this case what? This is minus 6, right? The first non-zero element in the second row is minus 6, and this is the new pivotal element. And what should I do? To guarantee that third row has more number of zeros than the second row, I need to turn this value into 0, right? This is what I should do. Okay, how can I do that? Okay, how can I do that? So in other words, I need to change the third row, and third row must be replaced by something else. By something else, I mean adding third row to some other row multiplied by some scalar, right? By some real value. How can I do that? I think about that. So I should multiply the second row that I can have a value 8 in this pivotal location, so that when I sum them up, when I sum the second row with the third row, if I want the value of 8 to be 0, then minus 6 should be minus 8, right? So what guarantees that? So in other words, I need to multiply minus 6, an unknown variable, say that x, and this should be equal to what? This should be equal to minus 8, okay? And this is actually the real value that I'm looking for to multiply the second row by, okay? And minus 8 over minus 6, the minus symbols are cancelled out, and if we cancel this by 2, we got 4 over 3. This is the scalar I am looking for. This is the real value, right? So if I multiply the second row by 4 over 3, alright, and then add it to row number 3 and replace the row number 3 by this right hand side equivalent, then I reach to my goal. And let's see what we got after this change. Okay, now the first row is the same, 1 3 7 and minus 1, and the second row again remains unchanged because I have not performed any arithmetic operation on that. Alright, so it keeps its values as it is. Okay, and what changed here is that multiplying, and the good thing is that, you know, if we multiply 0 by any real value, it is still 0, right? So which means that we don't lose any zeros that we already have found, right? Otherwise it would be very bad for us. Okay, and this is 0 because 4 over 3 times 0 plus 0 is equal to 0. Okay, and this is right, minus 24 over 3 is equal to 8, and minus 8 plus 8 is equal to what? Is equal to 0, as desired, right? We got the 0. That's cool. And here we got what? Minus 92, right? Minus 92 over 3 plus 23, right? And if we equalize the denominators, again, this is 69, right? And what we got here? Okay, and this is 69 minus 92. And this is minus 23 over 3, right? If we sum them up, this is minus 23 over 3. Yeah, we may find decimal values. It is very usual, right? It's normal. And again, 4 over 3 times 8, it is 32 over 3 plus 0, right? We got 32 over 3, right? And now let's check. We proceed and check whether or not we have a row echelon form. If we ended up with a row echelon form, then we stop our computation, right? As soon as we have a matrix in the form of a row echelon one, then we stop our calculation right at that point. Okay, now let's look at the case. Okay, we have 1 0 here. Now we have 2 zeros here, as desired, right? The number of leading zeros in the third row is strictly greater than the number of leading zeros in the second row, and the same thing is held between the first and second rows, then which means that we now have a row echelon matrix. All right, then let's look at the steps that we need to follow. Right, we need to first convert our n by n system into an augmented matrix form, as we did, right? So we have a system here in the original version, and we convert it into its augmented form, right? And we check to see if this augmented form is in row echelon matrix, and we notice that it is not. So we started to convert it into its row echelon form, which means that we perform 3 elementary operations, right? 3 elementary row operations to convert our augmented matrix into that of known as row echelon form. And when we have a row echelon form, we stop our computation. And then what? Now we are ready to find the solution, right? In the last step. Why are we doing this process? Why are we following the steps? Of course, to find the solution to the system, right? And by solution, what I mean, let's get back to our system again. Here's our original system, right? We started at this point. And what we are trying to find is this. We are actually trying to find the A, B, C tree tuple, right? The value of A, B, C that satisfies this system of linear equations simultaneously, and we're looking for a solution ABC such that it satisfies each equation at the same time. Okay, now we got our row echelon form. Then what we need to do is we use back substitution method, right? And how it is possible, right? We return back. Now we start at the last row. See, this is the reason why actually we separate the coefficient part from the right hand side, right? Because if you start at the last row, you see that, you know, this 0 is the coefficient of the unknown variable A, and this 0 is the coefficient of unknown variable of B, and this coefficient is the coefficient of the unknown variable C, and this value is the right hand side value. So this means that we have 0a plus 0b plus minus 23 over 3c is equal to 32 over 3. So these are already 0, right? We don't need to write them, but I'm just trying to indicate you what they are, okay, and what we have found, and how the things become easier now, right? Because it is just like, look at this equation. We have only one unknown variable. This is what I'm talking about. This is actually what I've been talking about since the beginning of the lecture series, okay? So we have only one unknown variable and one equation, okay, and it's very simple to solve it, and already 3's are cancelled out. So what is the value of C, right? This is actually nothing but 32 over 23. This is the value of C. So now we know what the value of C is, okay? And then we started to apply back substitution method after having the row echelon matrix form, and we move one step above to find the other unknown variable B. Okay, what you got here? 0a, 6b, right, in the same order, and minus 23c is equal to 8. Okay, so I know the value of C, right? So what is the value of C? I plug it here. Okay, this is already 0, I know that, right? And so if I put it there, 6b is equal to minus 8 minus 23 times minus 32 over 23, right? Because the value of the unknown variable of C is equal to minus 32 over 23, right? Right, I sent the 6b to the other side of the equality, and I moved the 8 to the left hand side of the equality, which becomes minus 8. I keep the minus 23. I put the value of C here, right? So these 23's are cancelled out. Minus minus is plus. So 32 minus 8 is equal to 24. And what we got is 6b is equal to 24. And by dividing both sides by 6, we got what? We got b is equal to 4. Right? And now b is equal to 4. I found the value of b, another unknown variable. That's good. That's the good news. Okay, let's keep doing. So where are we now? We have already found two unknown variables, which are the values of c and b, and that's only one thing left behind, right? Now I move one step above to the top row, and in the top row what I got A, right? I turn back, as you see. I substitute the values back because these are the coefficients of A, B, C. The third three values, the first three values are just the coefficients of the first equation, and the last value is the right hand side value. So I got A plus 3B plus 7C, right, is equal to minus 1. Okay, and this means A is equal to, right, minus 1, and move these values to the other side and leave the value A, the unknown variable A, alone on the left hand side. Okay, minus 3 times B, which is 4, and minus 7 times minus 32 over 23, because the value of C is minus 32 over 23. I don't forget the minus sign here. That's important, guys. You see, to avoid ourselves from making a numerical error, or without, for avoiding us to run into a computation error. We should be careful about that. Okay, let's keep doing. Okay, we got what? Now we got A is equal to minus 1, and this is minus 12, right? And minus minus again plus, and we multiply this 7 times 32, so plus 224 over 23, right? And A is equal to minus 13 plus 224 over 23, right? And now again we need to equalize the denominator, so the denominator here is 23, and I just multiply that. Okay, and then what we got? 23 multiplied by 13, we got what? Let's think about for a while. Minus 299 plus 224 over 23, right? And our final step, let's finish this. Alright, let's find the value of the last unknown variable, which is A is equal to what? Right, this is minus. We must be careful about that. So the result is minus 75 over 23, guys. Right, we found the last unknown variables. Alright then. Now, it's good news. We're done with our Gaussian elimination method, right? So just to summarize what we've done, we are given an original system as here, right? And then converted it into its augmented form, and then we perform 3 elementary row operations, right? We did the same thing on the system of equations by using equations, the same thing. And then we finally reach to a point where we have an echelon matrix form of the system, and then we applied back substitution method by starting at the last row and making our way to the top row and finding each unknown variable one by one. And this is the end of our solution, and the solution, say this is the solution set or solution. We were looking for an ABC 3 tuple, and here is the solution, guys. A is equal to minus 75 over 23, right? This is what we found. And how about B and let's remember we found B4, right? B is 4, right? B is 4. And how about C? And C, is minus 32 over 23. All right, then this is our solution, right? And this is the steps of Gaussian elimination method that we need to follow so as to find the solution of a given arbitrary system of linear equations. All right. Now what it means? Now, as you all remember, what we have found is actually we find a 3 tuple, right? Because why 3 tuple again? Because our system is a, you see it's a 3 by 3 system here, right? Because we have 3 equations and 3 unknown variables. But when we convert it into the augmented form, don't confuse with the 4 here, right? The column number, because we expand our matrix by the right hand side values, okay? But this original version is a 3 by 3 system, don't forget about it. Right, this is just the representation style that we use while using an augmented matrix. Right, then we reduce our system into an upper triangular one and apply back substitution to find the solution set. And this is how Gaussian elimination method actually works. Well, I hope you all enjoyed and understand how Gaussian elimination method is applied and why it is important. And as you can see, guys, we are given an arbitrary system. Now we're at a point to solve an n by n system in a very simple manner, right? A Gaussian elimination manner, a technique, by using this technique, because we're able to convert a given arbitrary system into an row echelon matrix form and then simply back substitute and find the values, in other words the solution set to that system. Alright, in the next lecture I will continue with the methods of solving system of linear equations, and in the next lecture we will talk about another well-known method called Gauss-Jordan method. But before that, we need to define and give examples about what is a reduced row echelon form is, and then we can start simply applying Gauss-Jordan method in order to solve a given arbitrary n by n system. And until then, have fun, guys. See you in the next lecture.